Yesterday, I started from this PDE. Here, rho is a function of x and t with x in or and t non-negative. And then I argued that if you take a classical solution to this equation and assume that the initial data itself is a solution to some ODE, then at later time you may hope that the solution would be the solution of a new ODE, and it's the vector field that is evolving with time, and I derive an equation for the evolution of that vector field. So if, say, initially, you know the derivative of this with respect to x, so treat this as a function of x, a solution to some ODE, with a velocity b0, then at later times, we may hope to have okay. And if this is the case, so this equation must be compatible with this. You have two equations. One equation says that how the space derivative of this is evolving. The other one says how the time derivative is evolving. Then these two must be compatible, and the compatibility must be consistent, and the consistency would lead to an equation for the function b. So here, b is a function of rho and t. Rho is any real number, and t is the time. Then call this 1, call this 2. So 1 and 2 consistent. This is equivalent to say that dB dt. So here I'm fixing rho and regard this as a solution to an ODE as a function of time. So this is a solution to an ODE, and the ODE turns out to be this guy. So for fixed rho, treat this as an ODE for b as a function of time. Then we observe that this ODE must be solved for the initial condition b0 rho. So if you fix rho, treat this as an ODE for function b as a function of time, then the initial data is b0 rho. And then depending whether b0 rho is positive or negative, you may have blow up or no blow up. Though for that, I need to make an assumption on the sign of this. So assume this guy is not negative, then if b0 rho is non-positive, no blow up. And we have a solution for all times. And if b0 rho positive, then finite time blow up. Okay, so makes sense. Things make sense. So well defined for finite time. That's what we observed last time. But then if you think about it, this is really the so-called method of characteristics for solving for finding the classical solution to this equation. So the fact that we have a blow up in certain cases, this is really equivalent to the occurrence of shocks. Okay, so after this observation, then I may wonder whether I can go beyond this. Namely, initially, if instead of having an ODE, maybe I have some ODE, and you may assume that B0 is always negative, for example, in the case that H is convex. Then once in a while, randomly in a Markovian fashion, I make a jump. And as we mentioned before, since solution to scalar conservation law with H convex, the entropy solution can have only one type of discontinuities, only increasing type discontinuities, then it's quite reasonable to take a Markov process for initial data that has only positive jumps, no negative jumps. Because even if that is not the case initially, then it would be the case at later times. So we may go beyond, let me call this 2. Maybe, well, this is 2, so this is 1.5 perhaps. May go beyond 1.5 and consider an initial data which is Markov with generator. So now rho 0, so the generator I denoted by L0. So think of X, the position now is kind of plays a role of time for the process that I have in mind. So you take H of rho. So rho would be the state. So you're really talking about the Markov process for which X is the time parameter and rho is the state. So therefore, I have to define an operator that acts on functions of rho. So there would be a drift part that has to do with this part of the story. Namely, you would have some B0 rho times H prime of rho. And then I want to have a kind of pure jump part that would make positive jumps once in a while. So for that, I need to start with a kernel. So let's take a kernel, F0 rho D rho star. So what it says is that once in a while, the state, which is the initial data, its value from rho is switched to some rho star. And rho star can take value only in this interval, because I want to have only positive jumps. And then the generator would take the difference of these guys. So again, it means that once you're solving this ODE, so let me draw a picture. So that's how rho star would look like. So you're just doing your business solving this ODE. But once in a while, you make a jump. As soon as you make a jump, then the initial data of the ODE changes. Then you have to solve the ODE again for this new initial data, so on and so forth. So if start with a Markov process of this form, based on the experience we had with the previous scenario, we may wonder whether this picture persists at later times. Namely, the solution, the random solution you get at positive time would be also a Markov process as you vary X, and its generator has the same structure. So we may go beyond and consider initial data. So we may wonder whether the process x going to rho xt is a Markov process with infinitesimal generator, which I denoted by LT h of rho equals a drift and a jump, but now for a new kernel. Okay, to succeed, I need to tell you how B evolves. So it's kind of, you have a family of generators, and you want to derive an evolution for that family. For that, it boils down to derive an evolution for the drift part and the jump part. And for drift part, I have an obvious candidate, namely this equation. So we expect and a certain evolution. In this case, would be some ODE for the kernel. Eventually, I'm going to derive an equation for this. But again, as we discussed last time, what's happening is that you may have different jump discontinuities, different shocks, and they run into each other. And therefore, the shocks are combined to produce a new discontinuity. And therefore, you expect this to have some kinetic flavor, like Smoluchowski equation. When you have clusters of different sizes, the clusters combine to form a bigger cluster. Though in the case of a cluster, you would have only the size of the cluster, and then you have this additive feature of it when you have sizes Z1 and Z2, and you get a new size, which is Z1 plus Z2. In this case, as we discussed last time, unless H is quadratic function, you don't expect to have an evolution that depends only on the size of clusters. Instead of a cluster, you should think of a pair of discontinuities. So the pair runs into another pair to form a new pair, and the evolution may depend on both right and left states of that discontinuity, not just the size of the jump you're making. Unless H is quadratic, you don't expect to have such a simplification. Okay, so that is the dynamics, but let's derive. So basically, maybe I should mention a conjecture, just a formal description of the conjecture. So Menon-Srinivasan conjecture basically says that this is the case. Namely, if rho 0 is as in, let me call this 3, as in 3, then rho t is governed by 4, and one can derive an explicit evolution equation for f and rho and b as in 5. I'm making progress. I don't have to go to half integers for my numerics for f and b as in 4. Okay, so that's basically what the conjecture says roughly. But now I want to give you a formal derivation of the equation you would get for this. So now, yes? That's right, a Markovian initial data. That's right. That's right. About the joint one? Okay, see, the dynamics is totally deterministic. So, and then you have a new Markov process when you lose information. So you start with some Markov process. At later time, you have this stochastic process when some information is lost. I think in principle, yes, you should be able to make such a calculation. Well, actually, okay, so you see there's some Markov. Okay, so this is very deterministic. So if you tell me what's going on at time t1, then I can condition on that. I can easily figure out what's happening at t2. So the answer is yes. Yes.
The Markov process, you're looking time as space.
That's right.
Space is time.
That's right.
So we are fixing one direction.
That's right.
What fixes that direction? What can't you occur in this direction?
Okay, so that comes later when I put more conditions on H. So what's happening is that that's a very good question. I mean, I have to worry about that later on. So when you talk about Markov process, somehow tacitly I'm making it kind of one direction positive and the other direction negative. Namely, in order to describe the law of the profile at any given time, you have to tell me what's going on at some x, and from that I have to determine what's happening on the right of x. So that's why there's a direction here. Now it turns out and I have to do that consistently for all times. At later times I have to play the same game. So it turns out that to make this practical, you have to make a further assumption on H. For example, if you assume H is also monotonically increasing, then what's happening that there's a shock moving to the left, and then it's in a consistent way you can always assume that the direction is positive. You don't have to change direction somehow. But if instead of increasing you assume H is decreasing, then you have to do it the other way around. Now, in general, maybe H is neither increasing or decreasing, sometimes increasing or decreasing. In that sense, you have to draw a line which is not a vertical line, and your initial condition should lie on that line. So you can always determine this. That comes when you decide what is the initial condition and what is the state at the so-called later time. And later time here means for larger x. Yes, so that comes later. Okay, but for now, I don't want to address that issue because there's so many issues that they kind of get mixed up. And I want to focus on one issue, and namely, how can I derive formally, find an evolution equation for f? But later, when you derive that formal equation, then you see some coefficients could be positive or negative. So you have to make a decision, what direction to go to make the coefficient positive. Otherwise, otherwise you have to talk about Markov process with negative rates. That's where it shows up, absolutely. Okay, so, but how you can formally derive an equation for f? So I think that's how they discovered this formula, Menon and Srinivasan. And actually in the paper, when you look at it, this is actually came to me as a surprise because I noticed the coefficients sometimes are negative and they never addressed it. After all, that was a formal calculation, but then you have to make further assumptions to resolve that issue. Okay, so we now derive an equation. We formally derive an equation for f. Okay, so I'm going to play the following game. So we have random rho xt. And now note that we have two equations, two dynamics going on here, namely rho as a function of x is Markov with generator LT, and then rho as a function of t solves the PDE, which you can think of it as rho t equals h prime of rho x. Okay, so think of it this way. But note that if h prime of rho is not 0, with kind of for formal calculation, I can pretend I can pretend that this guy never vanishes. And this is not a severe restriction. For example, I want to have h prime of rho to be positive always. Maybe that is not the case. But you can always shift the solution. You kind of translate it by linear speed. Then that would modify the PDE, and that would add a constant to h prime of rho. So if rho is in some bounded domain, then you can kind of, you have an upper bound, you have a bound on this from left and right. So adding if you add a constant to this h prime of rho, you can always guarantee that this guy is positive. And adding a constant to h prime of rho, it turns out it's just a matter of making a linear translation for rho. So somehow it's not a severe restriction. I discuss this later. But note that if h prime of rho is not 0, then we can think of it as rho x equals 1 over h prime of rho t. So for classical solution, I can write it this way. So it's as if we can also treat rho as a PDE for which the time and space are switched. Though there's some subtlety here, because for this PDE, I need to have the entropy conditions. And for that, it matters h is convex or concave. I'm assuming h is convex, so rho minus is less than rho plus. But when you write it this way, then the derivative of the flux is given by this guy. And if h is convex, h prime of rho is increasing, and therefore this guy is decreasing, which means this PDE, the flux is concave, not convex. Therefore, for this PDE, the left value should be bigger than right value. However, that very much depends what would be the positive direction for x. Now here it matters which way you're going. So in order to have the entropy solution for this new PDE as well, you have to solve the backward problem. You have to solve the final problem. In other words, you give me some x, then I have to go kind of less than x. So this, you have to take this with a grain of salt. You have to, if you write it this way, then you have to reverse space as well. Otherwise, you wouldn't have entropy solution. However, writing it this way, it suggests that perhaps if you fix x and vary t, maybe the solution is also a Markov process. See, in the previous consideration, I fixed t and varied x, and I figured that if you give me the value at some x, then I treat it as a Markov process, and I can determine the value for the right of x. But maybe I can play it the other way around. Namely, I can fix x and vary t, and hopefully I also have a Markov process. So now here we have an entropy solution provided that we look at not initial value problem, final value problem. Maybe this suggests that maybe this suggests that perhaps t going to rho xt is also a Markov process provided for fix x. So let me redraw my picture. So now this is time, and this is x. So I can imagine, so here at t equals 0, you have some random process, and then the profile is evolving with time. Then you keep track of what's happening to rho at this line. So I can imagine that as this equation suggests, you would have a certain ODE for this guy, for fixed x as t changes. And once in a while, a shock crosses this line that will force the value of rho to make a jump. So you do have some ODE part in the problem, plus a jump process that comes from all the shocks that crossing this line. So in fact, if this is the case, then we have a generator now. then T rho xt would have a generator, which you may say is the operator. So now I'm fixing x and vary t. Would be the operator m super x acting on h. So there would be a drift, but what is a drift? You see, if you look at this equation, if you ignore the jump part first, if I want to concentrate on drift part, I ignore the jump part. If you ignore the jump part, you know rho x is b of rho t. So I know that rho satisfies the ODE if I ignore the jump part. So this would be b of rho. And therefore, rho itself can be treated as a solution to an ODE as you vary t. But this time, the drift would be the old drift times h prime. So the first part, instead of this, would be h prime of rho, b rho t, h prime of rho. So that would be this. And the second part would be something like this. But now you have to figure out what happens to this guy. And first, I'm going to make a wild guess, and then I justify it. The wild guess would be that if here the drift is multiplied by h prime of rho, then maybe this is multiplied by a similar thing. But f is dealing with the jumps. And whereas this is the speed of characteristics, perhaps I have to put here the speed of the shock discontinuities. And therefore, here you expect something like h rho rho star sitting here. So that would be my wild guess for what this guy would be. And in fact, you can make some formal calculation, convince yourself that this is the case. However, for one thing, to make sense of this, I have to make sure that h is non-negative. So let's make that assumption. To make sense of this, we need to assume that h is increasing. And the way to understand it is that, so let's make this assumption. So assume h is increasing for now. And then I tell you how you can relax this condition. You can relax it, but if you relax it, then the form of this changes. And in fact, in that case, instead of fixing things varying x, you really have to look at the solution of, so the previous case was when I restrict the solution to the horizontal lines. And then here is when I restrict the solution to the vertical lines. But if h is not increasing, then instead of taking the vertical, the horizontal and vertical, you have to take the horizontal and some tilted lines, not necessarily the vertical line. That's the difference, okay? As I will discuss later. I want h to be increasing. H prime is already increasing. So I'm making a further assumption. I'm assuming that in the range of, so there's the solution rho. Let's say rho is in some bounded interval. In that interval, I already assuming h is convex. I further make this assumption that h is also increasing. So the kind of picture you have for h now would be in the range of the rho that I consider, my h is not only increasing, it's convex, it's also increasing. Say it again. H. This one you mean? Yes, that's the speed of the shock. I put the speed of shock there, and that is a positive number now. That's the speed of shock, yes. That's right. Oh, you mean this one? Yes. So you mean you're talking about the weak solution? Okay, so you see, this is a little bit formal. Nonetheless, if you take a solution here and treat x and t differently, in order to be a weak solution, all you need, so when you write the equation, necessary, if it's piecewise smooth, necessary and sufficient condition to satisfy the equation in weak form is that Rankine-Hogonian equation should be true. And let's see. Yeah. Okay. I think the answer is yes, but yeah, I could be wrong. Let me see. If I look at the, okay, so yeah, then that may not be true. So this is really formal level, but it just suggests that I have to check that. Yeah, you're right. But in any case, okay, so here I'm assuming if you assume h is increasing, then you can take any vertical line, and vertical line would be Markov. But I'm not saying that on every line would be Markov. It would be Markov if, when you do the calculation, the rate is positive, then it is Markov. Otherwise, no. Yes, you're absolutely right. Okay, so assume h is increasing, and then what is happening is that on a vertical line, we have an ODE with some jumps. The jumps come from shocks crossing that vertical line. In fact, the Rankine-Hogonian condition equation basically says that it basically says the location of the shock is given by minus h rho minus rho plus, and this now is going to be negative, which means all shocks are traveling to the left. So if you draw a vertical line, if you have a shock, if I draw the discontinuity curves, they all look like this. Something like that. So once in a while, a shock crosses this vertical line, and when that happens, then you make a jump on the value of the rho. So that's exactly what's happening. And this basically, the reason the speed shows up here, you have to do some formal calculation, namely, what's the probability that the shock occurs in some interval? So then you know that these random guys are waiting to cross this line. You basically calculate the time that it takes that one of these shocks cross this guy. And since the speed is given exactly with this shows up in the calculation. And when you do that formal calculation, after all, you just have a bunch of Poisson processes here, exponential random variables. When you do that calculation, then the rate shows up to be this. So formally, you can justify this. Okay, so far there is no theorem, but I have a kind of a scenario that I'm wondering whether this is true. So I'm going to make an ansatz. And assuming that ansatz, then I can derive formally an equation for f. So this suggests making an ansatz. So all this is just the following scenario. First, assumptions. H is convex, and H prime is positive. Okay? And then ansatz rho. So this condition is necessary to treat this as a Markov process. If I drop that, then again, I have to change this. Instead of a vertical line, I have to take some tilted line, which is not necessarily vertical. But if you make this assumption, then this ansatz has a chance to be true. So rho xt is Markov with generator LT, and rho xt treated as a process in T is a Markov with generator. Okay, so I take a vertical line, but the fact that H here is independent of position suggests that no matter what vertical line you pick, since the space is rather homogeneous, everything is happening in a homogeneous fashion, then when you fix X, the Markov process you get would be the same. So somehow it suggests that rho xt should be a Markov with a generator mx, but this is independent of X. Though the process would be different because the initial condition for this process at different x's would be different. But when it comes to the dynamics of that process, then the coefficient should be independent of X. Note that that is not the case with LT. LT would depend on T. After all, you're not at some kind of equilibrium or anything. You have rho 0 here. Then because of the very form of this, the ODE part depends on T. So this, okay, so if I want to compare the two, is that this LT for each T is an is a homogeneous Markov process, but that Markov process changes with time. Whereas this guy is an inhomogeneous Markov process. However, that Markov process doesn't depend on X. So the difference is inhomogeneity versus homogeneity. Yes? Because of only initial data, not the dynamics. Because the deterministic PDE is homogeneous in space. H doesn't depend on X. Yeah, because of initial data, you have a different process. Absolutely. But the dynamics, the rules would be the same because you have a different initial data. Absolutely. So this is an ansatz I want to make. Okay? Now, assuming this ansatz, and I want to do some formal calculation and suggest an equation for the evolution of this guy. So this is the guy that changes with time. This is independent of time. Once you determine the coefficients of this Markov process, you just use those coefficients and put it in here and have a candidate for what's happening for the other guys. So the question is whether I can derive an evolution equation for this. Now, how you can formally derive that equation? Well, if you remember, you started with this, assuming there is no jump discontinuity, then the fact that the mixed derivatives are the same, the fact that that PDE must be compatible with the ODE that you kind of use to describe the evolution for given time, the fact that these two equations were consistent allowed me to derive an evolution equation for B. Now I want to play the same game here, except that now the process I'm dealing with is a stochastic, it's not deterministic. So basically, so basically I have two Markov processes, put it differently. These two Markov processes should be compatible with each other, and that should lead to an equation for F. So how you do that? Now, to derive an equation for F, let us define. So I'm going to play the following game. I'm going to start with some initial rho. And then, so you start with some initial rho. Now I have two Markov processes going on. One of them is that as I change x, things evolve, and I would have a new density. The other one is as I evolve time, things change, and I have a Markov process. So let's change both and take some test function h. And let's take the expected value of this random thing with rho 0, 0 equals some initial rho. So, I'm kind of basically writing the semigroup formula. And call this wxt. Basically, I expect that, OK, so if you fix x and treat this as a Markov process for t, then this would be the semigroup more or less. And you expect wt would be LTW. If you fix t and vary x, then you expect wx would be MW. Okay, so kind of formally that should be true. But then I'm going to calculate the mixed derivatives to see what I get. I'm going to differentiate both sides with respect to x here. Then I would get wxt equals to, OK, as I differentiate this with no, I'm sorry. It's the other way around. I apologize. So again, if I fix t, treat this as a process of x, then semigroup property suggests that something like this is true. The derivative of that with respect to x should be the generator acting on function w. If I treat this as a process in t after fixing x, then the semigroup property suggests this. But let's differentiate the first equation, both sides with respect to t. Then on this side, one contribution comes from differentiating the generator with respect to t, meaning the coefficients of the generator with respect to time. So one contribution would be this. The other contribution comes from applying the time derivative on w. So I'm going to have wt. But wt is given by m. That's what I get if I differentiate both sides of this equation with respect to time. If I differentiate both sides with respect to x, I play the same game. So this, as I observed, doesn't depend on x. So I just have to apply the derivative here. And that can be written as LTW. If I match these two, I get some kind of formula that you may encounter when you study exactly integrable models. Namely, you learn that this operator, this equals to MLT minus LTM. So this is the kind of equation you get. You see, here, I'm taking advantage of the fact that m doesn't depend on x. If m depends on x, then here you should have the derivative of m with respect to x minus the derivative with respect to x. And this kind of reminds us of some of these exactly completely integrable models. However, this is explicit enough that you can kind of use all the formulas that I have. I know what m is. I know what LT is. Just plug it in here. Then I have one operator here, one operator there. I match the drift part. Then ODEs shows up again. Not surprisingly, after all, I derived the ODE using the same trick. And when I match the f part, that would lead to an equation for f. So using this, we arrive at one of them would be bt exactly the second derivative of b squared. So that would be one equation, which is not surprising. The other one would be something like this. But I'm going to, again, wait a little bit longer to reveal the very form of this, because the formula is going to be long. After all, that calculation is going to be rather tedious. But you can do that. It's straightforward. And eventually leads to an equation of this form. But I'm not going to tell you yet what that equation is, for more excitement. OK, so the question is, I forgot my number. That should be 5 or something. 6. What is the exact form of 6? You know, it's like somebody offers you some drink, you don't know what it is, just wait, you know. Later you want to have more reasons to try that drink. Is it poisonous or not? So I'm not going to tell you yet, because the form is rather tedious, and yes? Say it again? That's right. So, okay, so here I'm making several assumptions. One is this is of course a pretty serious assumption, so keep that. This is an assumption that I'm not happy about it, but it's rather harmless. That can be avoided, but to avoid that, instead of a vertical line, I have to choose another line. So that's another thing. But I'm making further assumptions that is tacit here, namely, if you want this to be valid for all times, you have to assume B0 initially is non-positive. Then the solution to this ODE never blows up. That's right. So, okay, I'm avoiding some technical issues. So the first scenario, the simple scenario would be initially start with B0, which is never positive. In that case, that stays the same at later times. And basically, that assumption really means that I let all the shocks to be the shocks that they come from this stochastic dynamics, not the shocks that comes from the PDE, from the ODE. So if you make that assumptions, then you have a simple scenario for which all this formal calculation, you can make it rigorous. However, if you drop that assumption, then you have to modify things a little bit. And this is still possible. However, the problem would not be a simple ODE and a kind of jump process that comes from the dynamics. Instead of a simple ODE, you always have to solve the scalar conservation laws, even for the B part somehow, so to speak. So if you just want to have an ODE to treat the B part, you have to make these assumptions. Otherwise, you have to do something else. Instead of solving the ODE, basically the ODE would not do the job, because every time a shock happens, a shock that does not come from the initial random shock. It comes from the deterministic part of the story. Then you have to modify this. Yes. Okay, so far so good. Okay, so, but since the form of this is rather complicated, I'm going to make further assumptions that would allow me to simplify that equation. Then it's something that I can share it with you. I can reveal that equation without scaring you. Okay? So as a warm-up, let us treat the case B0 identically 0 first. So I'm going to treat this case first, which really means that the ODE part is not there, and initial condition is just a pure jump process. So this means that B is identically 0, and initially we have a pure jump process. So rho 0 looks like this. Okay? And now in this case, several terms disappear from this description. Then it makes it easier to describe. In fact, I'm not being very honest here. Here, you also have a linear operator. And linear operator that appears here comes from the B part of the story. But if B is identically 0, the linear part disappears, and you can focus only on the kinetic part. Okay, so in this case, six simplifies. And takes the form Ft equals QFF. So it kind of has a kinetic flavor. And again, it's not surprising because what is happening is that the shocks combine and some kind of Smoluchowski type equation should govern the dynamics of F. And now I'm going to be more precise about it. More precisely, so let's look at this kernel. Maybe I write it like this. So this governs the jump mechanism. The total mass of this measure has to do with waiting time, the waiting time that it takes before you make the attempted jump. So suppose you're at state rho minus. Take the total measure of this kernel. That would be a function lambda rho minus, which means you integrate this part. That lambda rho minus is a parameter that says if you're at state rho minus, then the expected value of waiting time you have some kind of exponential random variable, and the parameter of that exponential random variable would be lambda rho minus, which is the total integral of this guy. Okay? So, but now I want to tell you how the derivative of this is evolving. So there would be two parts. One part is that under what circumstances I can produce a shock that connects rho minus to rho plus. And it's easy to figure out what that mechanism would be. So you want to kind of produce a scenario when you have some rho minus and rho plus, and that has been produced. So the only way you can produce a shock connecting rho minus and rho plus at some time t is that you used to have a shock connecting rho minus to rho star and a shock connecting rho star to rho plus. And these shocks happen at locations xt and yt. And since these xt, yt are kind of moving, then this takes over this guy. It runs into this. And therefore, this state shrinks to nothing. And then you have a state connecting rho minus to rho plus. That's the only way to produce such a shock. And now let's see how we can produce this scenario. Well, to have this jump, the probability of that would be f of rho minus d rho star. To have this scenario, you would have something like rho star d rho plus t. And the speed of this would be minus h rho minus rho star. And the speed of this would be minus h rho star rho plus. And therefore, so I'm assuming h is increasing or non-decreasing, which means this is negative, this is negative. So what's happening is that this guy is moving to the left, this also moving to the left, but because of the convexity, you see the size of this velocity is larger than the size of the other velocity because of this relationship. So remember, you have a scenario like this. You have rho minus here. You have rho star here. You have rho plus. That's the scenario you have. And the speed has to do with the slope of this chord. The slope of this chord is larger than this. So that says that this is just a matter of time. This is going to take over this guy eventually. Though in reality, you have many shocks. So this would took over if the other guy didn't reach it before. But kind of in principle, if you have only two shocks, that's exactly what's happening. So basically, the coefficient you put here would be the relative velocity. So basically, you have here h rho plus rho star rho plus. Maybe I put parentheses here, too many brackets. So that would be one contribution. But there will be further contributions. This is the scenario that you need to produce a shock connecting rho minus to rho plus. But then you may have rho minus and rho plus, and that shock is spoiled because some state from the left or some state from the right came and changed it. So there would be two further contributions. One would be that you go from rho star, rho plus to infinity. Some state on the right of rho plus comes and messes things up. And then the relative velocity, you put relative velocity there too, would be h of rho star rho plus minus h of rho minus rho plus. And then you have f of rho plus d rho star t times f of rho minus d rho plus t. And the last contribution would be rho minus infinity h of, so note carefully that the variable of integration here is just rho star. Rho star is always the variable of integrations in all the three integrals that I'm writing here. And the other one would be rho minus rho plus minus h of rho minus rho star here times f of rho minus d rho star t f of rho minus d rho plus t. So this is the kind of equation you have. So Q that appears there is exactly this quadratic form. Okay, now so now I'm kind of ready to say the theorem regarding the conjecture. The statement is very simple. The conjecture is true. Okay, so this is the joint work. But we did it in two shots. First, we treated this case, and then we proved the general case, because general case kind of far more complicated to write it down. But if you assume that initially you have pure jumps, then the theorem is true. But actually, you see, if you make these assumptions, namely H is convex and H is increasing, then as we observe, the dynamics for fixed x is also determined. It's more convenient to treat this PDE on the first quadrant. Namely, you really want to prove this PDE in the following way. So basically, you want to kind of, you see, since all the shocks move to the right, so if you can kind of solve the problem only here, and you don't have to worry about what's happening there. Because the shocks, if you have some initial condition with certain jump discontinuity on the left, they never interfere with what's happening on the right, because everybody's just moving this way. So basically, you want to say that, yes, I have a Markov process here. Initially, start with a Markov process there. Then the randomness of this Markov process would yield the Markov process here. Then you want to say, yes, I do have a Markov process on this axis. The generator is given by that formula that I mentioned. The generator would be M. And moreover, if you take any vertical horizontal line, you also have a Markov process for which the generator is LT. Basically, that's the statement of theorem, but I'm not going to write it down. And let me tell you, before getting to this part, which makes things far more complicated, so I'm assuming B equals identically 0. Let me tell you what is the idea of the proof. Okay, so let's review some of the techniques that have been used to treat this kind of problems. I mentioned the work of Grunbaum and also Bertoine. Bertoine treated this case when H is quadratic and initial data is Levy. The way he proved it, the way he proved the theorem, he used the variational formula for the solution to the PDE. And using that variational formula, there would be some minimization problem to do. And you look at the minimizer, you say something about the minimizer. So basically, the problem boils down to have some Levy process adding some quadratic function to it and looking at the maximizer or minimizer. And Grunbaum treated the situation when the initial data was white noise. If you start with a white noise, immediately becomes a Levy process with increasing jumps only. He never mentioned PDE. In fact, he was interested in a problem that came from statistics when you needed to know what the convex hull of a Brownian motion perturbed by a quadratic function would be. And he figured out what the law of the minimizer is. But if you translate it to the PDE, that would be the same as having a Berger's equation with white noise initial data. So they all used the variational formulation of the solution to the PDE. In fact, they didn't bother with the PDE. They just treated the minimization problem directly. But the way we treated the problem is completely different. We basically treated the problem as a particle system. So here you really have a particle system with a very deterministic dynamics, and you start with some random initial data, and then you have a candidate for what the state would be at later times, and you want to show that that random dynamics is compatible with this deterministic dynamics. That's basically the way one can treat this. So let me say something about the idea of the proof before I get to more complicated situations. So there are two sides of the story. One side is that you basically have a particle systems. So let me describe the dynamics of the particle system. That's the PDE part. So okay. So if initially we have a pure jump process, then the profile is really a sequence rho 0, x0, rho 1, x1, rho n, xn with x0 equals 0, rho 0 strictly less than rho 1, strictly less than rho 2, and maybe I write it this way. X0 is 0, strictly less than x1. Here, xi is the location of the ith shock, and rho I has so let's have a convention here. So here x0 is 0, and here I have x1, x2. So this would be rho 0. The value. So you kind of look at the problem on the left of the origin. So the value you have here, you call it rho 0, you call this rho 1, rho 2, so on and so forth. And the rho I, therefore, would be the right value of the solution at xi. So it's really rho xi plus t.
So you don't allow infinite number of small shells?
No, no, that has to do. In fact, I'm going to make an assumption. OK, so I wrote an equation for this, but I haven't told you how you can prove the existence of solution to this differential equation. This innocent-looking thing is very hard to play with. After all, there are so many things involved here. However, if we assume that the initial kernel, its support is in some bounded interval, then that picture persists at later times, and you can prove the existence and uniqueness of this ODE. So I'm making that assumptions. That means all the jumps, all the states, rho i's, happen in some finite interval. Okay? But no, rho I could be anything. But some interval, some finite interval. So it's as if the initial condition that I have in mind would be bounded from below and bounded from above. Not really. So let's treat it in fact, the way we treat the problem is that, okay, so what's the, you see, basically, what I'm trying to say is that the jumps, it takes longer and longer to happen so that rho never can go up. So I have to make that assumption. Otherwise, you see, it wouldn't matter really, but if you can prove. That's right. No, yes, I'm avoiding that. But I'm saying that is hidden in the assumptions I make on the kernel here. And if I don't make that assumption, I don't even know how to prove the existence of solution here. So I make assumptions on the kernel so that no small jumps, not too many small jumps are allowed. Okay? So therefore, I can order it exactly. So basically, I'm assuming that for the first jump to occur, I really wait a while, and then it happens. Right. Not like the Levy process when you can have very small jumps. Now, I'm avoiding all that cases. Otherwise, I don't know how to even make sense of this. OK, so this is kind of the state. So I can forget about the PDE. I just have a collection of numbers that are all ordered. And then I have the law of this state initially, because I have that Markov process. I have all these waiting times, and you make a jump. So all that is given. So and then so this is the state. How about the dynamics? So I have to kind of figure out what the dynamics is. So the dynamics consists of several things. One of them is that you choose some random initial data here. That would be your candidate for rho 0. No, I'm sorry, that comes later, but it doesn't matter. So suppose that I already know what rho 0, x1, rho 1, x2, so on are initially. So suppose I know what this guy is, and I want to kind of design a dynamics for this. The dynamics should be compatible with a PDE, and I have an obvious candidate. So the candidate is that first, each xi travels according to a velocity, and the velocity of xi is simply given by minus h rho I minus 1 and rho I. So that's one part of the dynamics, just particles traveling to the left, and the speed using the other part of the configuration, the rho part of the configuration, I figure out what the speed is. So that's one part of the dynamics. And the second part of the dynamics says that when two xi's run into each other, then one particle is lost, and the corresponding rho i's are combined. So basically, what I'm saying is that if x2 reaches x1, then this guy disappears. Now you have the state that connects rho 0 to rho 2. And then you have a new location. So the other part of dynamics says that when xi collides with xi plus 1, then one particle disappears. And one particle disappears, so meaning xi rho I disappears. Okay. But actually, in reality, I need to add another dynamics, because it's kind of hard to solve the problem in infinite line. So I'm going to draw some line on this side, and then I add a further part to the dynamics, which says that in a random fashion, once in a while, a particle creates right at the border. And where the particle comes from? The particle comes from this side. And this is when the shock crossed there. And I have a candidate for that Markov process would be. So in reality, for the real proof, I really have to cut off the whole process on infinite line and turn it to a problem in finite line for L very large, and put kind of a stochastic dynamics here. But I'm not going to discuss that, because that's a technical issue. And I pretend that I just have a dynamics in infinite half line, and the dynamics is only deterministic. So let me make a comment. We may Maybe I make this comment later. For now, accept this. So that's the dynamics. So I have a candidate for the dynamics. And OK, so however, let's see how much time I have. So I'm just kind of designing things in such a way that right at some exciting point, I want to stop the story. I'm kind of like, no, I still have time for some not very exciting things to discuss. OK, so often when I teach at Berkeley, I usually end my lecture in the middle of a sentence even. And then I put some dots for more excitement. Let's see if I can manage to do it here. No, I teach in a public school. You really have to entertain people. Just a habit after so many years of doing this. OK, so now, in fact, so the dynamics is totally deterministic, but imagine that I start with some random initial data. So if initially, maybe I have a name for this sequence. So let me call this Q. So if initially Q0 is random, then Q at time t would have a law, say fqt, then basically what's happening is that this law is defined for those xi's that are ordered and rho i's that happen to be increasing. And basically, then you can kind of formally write an equation for this. Basically, what's happening is that this f must satisfy the following equation. Ft plus the sum of those velocities must be 0, deterministic dynamics. However, this f would satisfy certain boundary conditions, and that would be very important when you want to make things rigorous. And you basically want to say that at a collision, when a collision happens, this f right before the collision and after collision should be the same. So that would be a boundary condition. So if you kind of have some experience with Boltzmann equation, that's exactly what happens there too. So basically, you want to say f of, because kind of the kind of dynamics you have here is rather discontinuous, because when a collision happens, then the velocity, not only you lose a particle, the velocity changes. Because after collision happens, then you have new states, and based on new states, you have to adjust the velocity. So basically, you want to say that f qt plus t plus equals to f of qt minus t minus when a collision happens for some I. Okay, so that's the dynamics, and this is a kind of mathematically you can describe it in this way. The law of Q would satisfy some very simple differential ODE, but the non-trivial part of the story is that this law would satisfy certain boundary conditions. Make sense? So that's one side of the coin. What do you see on the other side of the coin? So that was one. So this is one side. The other side says that this conjecture offers a candidate for what fqt would be. Now I have a candidate for it. Namely, if Q is distributed according to L0, then, though I have to translate in terms of xi and rho i's, that I can easily do. Because previously I regarded it as a process, but now instead of a process, I just have a collection of numbers. Then Qt has a law that is determined using its initial condition. Initial condition means what's happening. This is what I have here. What's happening here? If I know exactly what rho is, that's the initial condition of my Markov process, then I can kind of determine the law because I know what the dynamics is. Using its initial condition, rho position 0 and time t, and its generator, LT. In fact, using M, so remember M is the Markov process you see here. And I know I have a candidate for what M would be. So in fact, using M, we have a candidate for rho 0 t. So rho 0, so this guy is rho 0. Rho 0 stays constant, but when the shock crosses, it makes a jump. But I have a kind of a candidate for it. So let's say you have some initial. So you have a candidate for rho 0 0. That would be the initial condition for this rho 0. So rho sub 0 means the value of rho when position is 0. Rho super 0 means the value of rho when time is 0. That's what sub and super means in this business. So there's this rho 0 that it changes with time, and you have a candidate for its evolution, M. You have a candidate for its initial data, whatever the solution is at 0, 0. Using this, then you can determine the law. With this initial condition, you can determine the law of rho 0 t at later time. So you can for, say, L d rho 0. So I have a candidate for the law of this guy at given time t. Then Qt should have a law of the form. So let me write down a candidate for what that law would be. I have a kind of obvious candidate for it. So Qt consists of a bunch of locations and bunch of states. And I want to know with what probability you see certain rho i's and certain xi's. I want to write down what that probability measure is. Well, initially, rho 0 happens with this probability, which solves the forward equation associated with generator M. And once you know what rho 0 is, then you're going to wait, meaning for the x parameter, for a while, using the total mass of the kernel that comes from the solution to the ODE. So you solve this ODE for f. You have a candidate for f rho minus d rho plus t. Then its total mass is given by lambda. So you would have, so if this guy is x1, then this is how long you have waited before you make a jump to rho 1. So that waiting time would produce, since this is an exponential random variable, would be minus lambda rho 0 times x1. That would kind of tell you how long to wait. That would take you to position x1. But once you have position x1, you make a jump to rho 1 using the kernel. Then you multiply this by kernel. That would take you here. While you are here, you wait for x2 minus x1 to make a new jump. So that would suggest another factor of the form minus lambda rho 1, x2 minus x1. Then you make a jump from rho 1 to rho 2, so on and so forth. So you have a candidate for what the law of the sequence would be, where here, so here, F is a solution to the ODE. And lambda of rho minus is the total mass of this measure. Of course, this in principle may depend on T, but it turns out that one can show this lambda is independent of T. That comes later. I discuss that later. But for now, I'm not ruling that out. So let me put T here. OK, so the other side of the story is this. The conjecture suggests the following law for the profile QT. Solve this differential equation. Look at the kernel, calculate lambda. Using this kernel and its total mass, write down this measure. This is a candidate for the solution to this. So all I have to show is that indeed this guy satisfies this differential equation. That's all I have to show. That's the end of the proof. Though to make this work requires some work, because you see that dynamics is a jump, is not even continuous. You make a jump here, and formally, to derive this equation, you have to differentiate something. So things don't work in the way that it may appear, but it turns out in principle, that's the idea. OK? Oh, I still have 7 minutes, something more exciting. Okay, so far so good? Yes? Yeah, I mean, no, the weighting would be longer, the kind of F that I have in mind. No, they're not higher. They're smaller. I mean, I want to make sure. So this is a technical assumption that I need to make here. Namely, the profile you construct would be a bounded solution to the PDE. I want a bounded solution to the PDE. So no matter how many jumps I make, I don't want to pass certain levels. That's right. Right, but it takes much longer time to get to something higher. Actually, yeah, you're right. OK, so maybe I wrote a differential equation. That differential equation makes sense for any kernel. But when it comes to proving the existence and uniqueness, I don't know how to prove it in general. So I make a further assumption. Namely, I look for the solution that initially the support is just some finite interval. So it's true that the kernel goes from some rho to plus infinity, but I chop it off. I assume that support is some big M that works no matter what rho minus is always, never goes beyond some big number. Some fixed, could be big, but fixed number. Otherwise, I don't know how to prove the existence of solution. OK, so no, I mean, so you have some kernel, right? That would be a kernel from rho minus to rho plus. First, rho minus is always in some finite interval. And no matter what rho minus is, I don't allow rho plus to cross some number. In principle, you can define such a measure, which means when rho minus is high, then you wait a very long time, but just you make a very small progress. It's possible. Yes. OK. Of course, you should be just constant, right? I think so, yeah. You would have only one shock. But even that shock is going to cross the origin, and that's the end of the story. So it would be constant profile. It would be just constant profile. Yeah. Right. So start with the initial data. Look at the, well, there is no last one. I mean, you just wait longer and longer. But in principle, yeah, right. I mean, you kind of, eventually you would have nobody here. However, again, to make the proof works, I really shut it off and just study here. So the dynamics now is finite, though you have some boundary condition here. I'll kind of tell you with what rate you enter from the other side. That's right. Yeah, yeah. So you have a creation of particles on the other side. Yeah, you create a particle. Right. Make sense? You see, I'm afraid I didn't do calculate things properly. You know, I have 3 minutes, even for my jokes, all my jokes. Good question. No. I mean, I don't have a good explanation why this is the case. I don't know why. It works, but can I explain it, why it works? I don't know why. Because you lose information. So in principle, there's no reason it stays Markov, but it stays right Markov. Good question. I mean, if you figure out what the answer is, let me know. I haven't figured out why this miracle happens. See, people previously believed that miracle happens for Berger's equation because Berger's is Berger's. But now this miracle also happened for this general Hamiltonian thing. And the reason I got into this, because I had other things in mind, there are also some conjectures when you add an external force. That's the case that I was interested in, really. But you know, now that we understand this, I think we have a chance to look at that conjecture also. With external force, that would be the most interesting part. This is like Berger's plus some external force that depends on space and time. Then you can ask what the equilibrium measure for that guy is and all that. Okay? So I guess I don't have much time. You know, yes, you can ask for. Self-similar solution. Yeah. That's a possibility, but you know, I don't understand that kinetic equation that well. It's very hard to play with it. I think if you develop a better understanding, then you have a chance, because the same thing happens with Simonovsky equation. You can have self-similar solution to that equation. You know, maybe you have a chance for this guy as well, but yeah, I don't know the answer. That equation, anything I want to prove for this, I have to work very hard, because somehow we don't have a good feel for it. But something interesting happens for that equation, namely, in this case, this lambda rho 0 is independent of time. So you see, for a Simonovsky equation, it's the mass that is conserved. Here, this equation, mass is not conserved. The total mass of the probability measure is conserved. So something that is rather strange, but is true. So therefore, you can drop t here. And once you drop, in fact, if initially assume lambda rho 0 is independent of rho 0, then that picture persists at later times, and that would allow us to simplify the differential equation. This differential equation simplifies if you make that assumption. So it's kind of more friendly when you make those assumptions. So, okay, so I have to make a decision what to do on Friday. So one possibility is to say more about this. The other possibility is like change gear and discuss something completely different, but it's still for Hamilton-Jacobi and Scalar Conservation Laws. Now, normally I wouldn't do that in a class, but for an audience like this, I can ask for a vote. So let's see, how many people want to hear more about this? Raise your hand. I know if you do that in a calculus class, the outcome would be disaster, because nobody raised hand, because nobody want to hear anything. But here, I think for an audience like this, so you know. So how many people want to hear about matter theory for Hamilton? increasing. That's right. If it's not positive, you see it's the same picture, but the initial condition would be a line like this. So you treat the particles when they cross this. Okay, you see, I never looked at the long-time behavior here. I'd rather look at the long-time behavior when you add an external field. I think here, the picture is not that, I'm not sure you can have something interesting going on there. Eventually, you basically see constant in some big interval. So not really. Okay, I forgot about the outcome of the vote. So there are two choices here. It's not like Trump or Clinton. It's completely, it's kind of, I think no matter what you choose, the outcome would be better than the other elections you have to deal with. So either more of this, so many people vote for that, or the matter theory and Hamilton-Jacobi. Okay, so we are going to discuss something else. Though I hate not telling you what the equation is in general, but it's okay.